Alright, so this analysis and design is going to be dealing with page replacement. So the problem that we're going to be given today is that we have a given code fragment and we need to decide which page replacement scheme, whether it be FIFO, OPR, LRU, or MFU, should be used to optimize the performance of this code. So a little bit of background, the code itself, what does it actually do? Well, we're given two matrices, and those matrices are passed into a method, and the method is going to be checking to see if those are the same matrix. The first thing that it does is it checks that if either of the matrices are null, then it returns that it is not the same matrix. The next thing it checks is that if the number of columns or the number of rows are not the same, then they are not the same matrix. And then the next thing is if any of the individual elements in any of the rows or columns are not the same, then they are not the same matrix. If it passes all those tests, then it will return an integer value, which indicates that it is the same matrix. So the different types of page replacement schemes that we can have are FIFO, which is first in, first out. What happens here is that when a new page is needed, it's going to cycle out the oldest page. So whatever went in first is going to be the first thing to get removed. The next thing is OPR, which is the optimal page replacement. What this one does is it pays attention to what's coming up in the schedule ahead of time. So if it sees that a page is going to be used again shortly, it will keep that page. But if it sees that a page will not be used for a long time, then it will get rid of that page. LRU, that is going to be least recently used. So what happens here is that the page that is least recently used is going to get cycled out. So if it hasn't been used in a while, it's a goner. And the last one, the MFU, that's the most frequently used. What this one is assuming is that if you're using a page very frequently, then you're probably not going to need it again for a while. So it takes the one that was used the most and it's going to cycle it out. So some of the assumptions that we can make is that we're not going to know the contents of the matrix ahead of time. If we're going to be using this method at all, then that means that we do not know what's in them, so therefore we need the method in the first place to check if they are equivalent to each other, or else we wouldn't need them. The queue is going to have a fixed number of entries, which means that we can only have a certain number of pages in our queue at a time to be comparing. And finally, the performance is generally probably going to be decreasing as matrices sizes are going to be increasing. This is going to be potential for increasing a number of faults, again, because we're going to have the same number of queue size. Then if the number of matrix elements increases, then that means that we could potentially have a lot more faults than normal. So some of the requirements that must be met during this design is that our program has to, or the page replacement scheme has to use the data efficiently. That means that it's going to need to optimize the data usage so that it limits the page faults, such as the OPR, where it checks ahead of time to see whether or not it's going to be using an information before it gets rid of it. It has to be simple to implement. So whatever we create or implement, it has to be straightforward. It has to be usable within our scheme. And finally, it has to maximize performance. So it needs to limit the number of faults because the more faults it has, the worse the performance is and the slower it takes to progress through it. So some of the metrics that I want to be talking about are, again, the metrics are maximizing performance. I believe that's going to be the most important one that we have here. I'm going to be weighting this one at a 45%, and what this means is that it is the most important that we maximize the amount of progress that's being made by limiting the amount of faults. This is going to be increasing the number of speeds, and it should be working with infinitely large data structures. The next important thing is being simple to implement. If we can't implement it, or if it's very difficult to implement, then it may not be the best use of our time. So this one I've weighted at 30%. And finally, weighted at 25%, I have the data usage, and that is going to be optimizing the data. Sometimes a page replacement scheme may still be able to perform relatively well while not really optimizing the data. So therefore, this one is the least likely. So how are we going to evaluate this? Well, using each of those metrics, we're going to give each of the different page replacement schemes a score from 0 to 10, of 10 being the best, and we're going to throw it into an equation where we multiply it by their weights to find out which one is going to be the best of them all. So when we compare each one of them, what we notice is that FIFO, the first in, first out, it tends to have an average performance, but because it does not use the data very efficiently, it just cycles in and out without really recognizing a pattern. It's just sort of a run-of-the-mill, but it is very simple to use, so that tends to be the best case that it has, is that it is simpler to implement and use than all the other programs. But again, the performance, it's average, but the data usage is below average because it does not optimize the data. So this one ends up at a ranking of about a 5.7. The optimal page replacement. So what this one does, again, it checks ahead of schedule and double checks to see if it's going to be using data in the future or not. And for this one, the performance, it's very good. It's much higher than all the other ones, so therefore the performance is ranked at a 9. The implementation, though, the problem with OPR is that you need to know the data ahead of time in order to even implement or use it. And in this case, we've already made the assumption that because we're using this method, we will not know what the matrices contain. So therefore, this one will be impossible to use and implement. So therefore, this one received a 0 for the implementation. And finally, the data usage. So again, this one uses data better than all of them. It checks ahead of schedule. It's going to limit the number of faults. So this one received a 9. So even with that 0, it still received a score of a 6.3. And the least recently used. So based on some research that we found, it actually does a 20% less faults than the FIFO page replacement scheme, but it does not run into the Belides anomaly like the FIFO. So FIFO, the Belides anomaly, is where you can increase the number of elements in a queue and the performance will actually still decrease. Well, the LRU does not run into that, so therefore its performance is pretty good. It's about a 7. The implementation, it can be a little bit tricky, but it's not too bad. Usually it may need a way of tracking the last page reference, and that can be the trickier part of it. But it's about average, it's about a 5. And finally, it's data usage. So in this case, it's a little bit above average because it is optimizing the data. It is managing it and frequently checking and using a way to check whether or not the data is being used or not going to be used, and therefore making a decision based off of the data that it has to keep or not keep the data. So this one ended up with a 6.4, therefore getting a little bit higher than the OPR. The most frequently used, it's pretty close to the LRU. I put it at a 6 because it has the potential to work really well, but it tends to have a performance hit when it's dealing with large numbers of data. So it does tend to work better for small numbers of data that has less elements that are accessed more frequently. The implementation is very simple. The only difficult part that may be a little bit tricky would be adding a counter, but even then that is very simple, and therefore it has a higher ranking of implementation at a 7. And finally, the data usage. So it's at about a 5. It's good, it's not great, and it works for specific scenarios where there's repeating elements, but for the most part it manages the data, but it doesn't do anything super special. So altogether, this one ranked at a 6.05. So the central theme that we're looking at is that the algorithm performance is the key and main differing factor between all the elements. Or the algorithm performance is key, but the main differing factor is the implementation. So again, the first in, first out, I had a great implementation. It's very simple, but the performance and the data usage that brought it down below everything else. The OPR should have had hands down the best score, but in our case where we do not know the implementation, we do not know the data ahead of time, the implementation becomes impossible, which drops the score down. But otherwise, the performance and the data usage was far and above everyone else. Least recently used had above average performance, the data usage was good, and the implementation wasn't too difficult while maintaining a simple way to keep track of information. The most frequently used, it's similar to LRU in performance, but it's better used for small data, which drags it down. And the implementation, though, would be a little bit simpler, which brings that score up. So what can we finally bring it all together? Well, based on our chart, our information, our analysis, we know that if the data in each of the matrices was known ahead of time, we would be able to say that it was going to be OPR. But because we do not know the data ahead of time, what we would have to consider is the LRU would be the best in our circumstance. It does give us above average performance. It's a little bit easier to implement, and the data usage is above average. So therefore, the LRU would be our best bet for this scenario.